My name is Yudong, and I'm co-founder and CTO at Zapata. Joining me today is Travis Scholten from IBM Quantum. Travis has been working with us in the past year deeply on several efforts, and we have been enjoying the collaboration with IBM Quantum on using the tools and how that can integrate with Zapata products. So we would like to talk to you about some of the works that we have been doing with IBM Quantum on not only running application on physical hardware backend, but also what kind of extra information we can learn about the hardware through running those applications. So for the particular project, we chose this problem where the setting is such that through classical processing, we can iteratively reduce the number of variables involved in the problem and therefore reducing the number of qubits. And then these problem instances with various numbers of qubits are then solved using a quantum computer coupled to a classical computer. And finally, the data from the instances are then aggregated to show how the performance of the algorithm increases initially due to increasing the amount of requested quantum resource, and then decrease as the noise and decoherence starts to play a role. So in other words, we have realized a hybrid quantum classical workflow where a quantum device is seamlessly integrated into a set of classical processes. Because we need to handle the multitude of classical and quantum software tools that are involved in pre and post processing, as well as the iterative processing between the quantum and classical computers. There are architectural challenges that arise in this scenario. The first is framework compatibility, which becomes an issue when one is grappling with multiple paradigms of quantum computing, such as those proposed by IBM, Microsoft, Google, Rigetti, etc. And also, many of the quantum applications require heavy simulation efforts. So deploying these applications on cloud computing resources will also be an issue. And we also want to store and visualize data that comes out of the HPC execution in a principled way. And finally, we want to generate software that is reproducible not only by ourselves in the future, but also our team members and colleagues. So to overcome these challenges, one needs a modular, extensible, and reproducible software infrastructure. And let me also remark that this hybrid quantum classical paradigm applies across a variety of applications. So from our past exploration, for example, in quantum chemistry, it is widely known that one can deploy a hybrid scheme where if there was a simulation of a large molecule, one could perform coarse graining procedures that distilled the computational, the essentially challenging components of the quantum chemistry problem that is most suitable for quantum computers, and largely handle the remaining of the coarse graining procedure classically. So examples like this are QMMM and DMET. And in optimization, which is what we're going to talk about today, we have the concrete example of variational quantum factoring that also fits in this hybrid quantum classical paradigm. And also in machine learning, we've also experimented with different schemes, such as hybrid quantum classical neural networks using generative adversarial networks. So I want to talk a little bit more about the particular example that we consider in this project, which is the variational quantum factoring. So the overall problem of factoring is to start from an input biprime n, and the goal is to find two prime numbers p and q that multiplies to n. And the overall method starts by rewriting the factoring problem into a set of constrained equations, and then classically reduce the number of variables iteratively through pre-processing. So there are these low-hanging fruits that we can knock out. That there are variables that can already be filled classically by simple inference. And then the remaining variables, which we speculate are the challenging core of the problem of the factoring instance, is then converted to the problem of finding the ground state of a k-local Ising Hamiltonian. And this is a prototypical type. It's a prototypical problem that people have considered with near-term quantum optimization heuristics such as QAOA. And we adopt QAOA to solve these local Ising Hamiltonian ground state problems, and then glean the answer from the measured bit strings together with classical post-processing. So there are a couple key points on VQF that I think is worth highlighting. The first is that it's different from Shor's algorithm. I think every time if we mention quantum factoring, this is probably the first algorithm that comes to mind. The particular approach of VQF does not use the number theoretic structure that algorithms such as Shor's algorithm typically take advantage of. But there are interesting aspects of this particular approach, since it gives rise to these four local Ising Hamiltonians, which is in some sense beyond the scope of most of current studies on QAOA, which largely focuses on solving max cuts on D-regular graphs, and they give rise to largely two local Ising Hamiltonian. So when we look at the space of four local Ising Hamiltonians, we're firmly in the territory of what hasn't been thoroughly benchmarked with the current literature. And our initial effort, which was documented in the paper reference at the bottom of this slide, shows that empirically the scaling, the scaling of the total cost, including classical pre and post processing, together with quantum circuit training, it does scale favorably empirically. For more, one can look at the papers for numerical results. So to enable this type of VQF calculation, which is a hybrid quantum classical scheme, so how do we build a quantum software environment that allows for a deployment of this type of workflow? So this is sort of the practical problem of how do we actually implement this. And to describe what the approach that we take looks like, let's start from the library code. So these are library programs that are written in any language, such as C, C++, Python, Julia, etc. And this is perhaps the layer that most scientists and software engineers are familiar with. And at runtime, one can execute these library functions in a container environment, which is a lightweight local file system that allows a piece of code to run regardless of the underlying operating systems. And each container may produce artifacts that are data files that can be ported between different containers. And finally, the containers are orchestrated to perform a specific task that is described by a workflow, which are the workhorses of the quantum software environment. So these are some of the approaches leveraged in our quantum workflow product called Orchestra. We have built for a diverse range of library functions, including quantum programming paradigms and also domain-specific packages. And we have also integrated various hardware backends so that during runtime, one could easily switch between a diverse range of hardware choices. And there are also additional benefits to post-processing the data artifacts coming from the workflow with a variety of database endpoints for visualization and analysis. So in summary, the goal here is to enable scalable composition, execution, and analysis of quantum applications. And we probably have heard a lot through this conference about hardware agnosticism. I think the software philosophy adopted here is that we want to not only be agnostic with respect to the hardware, but also we want to adopt agnosticism across the entire stack. And the overall business objective is to de-risk quantum capability building and avoid vendor lock-in. We're very excited to integrate and have collaborated with the team at IBM to integrate Qiskit and related functions for IBM backends into our quantum engine, so that not only we are able to execute workflows running on IBM hardware, but also users of Orchestra can tap into the features enabled by Qiskit too. So next, I will hand over to Travis to speak more about the IBM quantum systems and what we have learned from the data collected from the various quantum backends.
Wonderful. Thank you so very much, Yudong. So what I'm going to be talking with you a little bit about is the systems that are made available by IBM Quantum, upon which we have run variational quantum factoring, and share some of the results of our investigations. So the system that we chose to investigate is called Berbligen, and Berbligen is based upon the Penguin family of processors. And I'd like to unpack that statement just a little bit. I'm sure as you read in the literature, you hear about different processor names such as Berbligen, Ruschlikon, Yorktown, Almaden, Johannesburg, etc. So each system that we build is codenamed with a particular city name. But there's various kinds of technologies and technology families that go into building different quantum computing systems. And we codename those using bird names. So as I said, Birdligan is based upon the penguin family, which is based upon square lattices with varying kinds of connectivities. And shown on the left-hand side of this chart is a plot of the C0 error rates across different revisions within the penguin family. And we find that as we change properties of the connectivity map, how our qubits are coupled together, that actually impacts those C0 error rates because errors such as crosstalk or spectator errors can be reduced. I'm not going to talk about other kinds of families of systems that have been built by IBM Quantum, but I would like to share with you the fact that in September of this year, IBM Quantum Vice President Jay Gambetta wrote a very wonderful blog post on the IBM Research blog talking about the future of IBM Quantum hardware. And it discusses some of the various kinds of families of systems that we are prepared to build and are currently building. Now, on the right-hand side of the plot is a connectivity map of Birdligan. It shows which qubits are physically coupled together using resonators. And this is significant because, as we see on the next slide, we can find that different qubits have different error rates and that the couplings between different qubits have different associated error rates as well. And so when we look at this plot, each circle is filled in with a color to indicate a single qubit error rate, and each line connecting different qubits is the error rate for a 2-qubit gate. And these error rates are typically estimated using randomized benchmarking. On the sides of the plot, you will see the readout error rates. These error rates are significantly important to consider because sometimes you might actually read out the wrong bit string from your quantum processor. And of course, you would like to minimize the probability that that occurs. Now, when we think about running VQF on the Birdligan system, there are a couple of, I would say, special things that it's worth keeping in mind. So as Yudong said, in the context of VQF, the output is a bit string that encodes a possible prime factor for an integer. Well, if we have the wrong bit string that we read out, we might actually get the wrong prime factors. And so minimizing readout error rates is very, very important for accurate results for VQF. The other is the fact that VQF uses the quantum approximate optimization algorithm. And that has a certain circuit with a certain kind of structure associated with it. And so therefore, the mapping of the virtual qubits in that abstract quantum circuit onto physical qubits on the Birdligan system is important. And maybe you've heard statements in the literature about circuit transpilation, circuit routing, etc. And those are the kinds of things that I'm talking about there. How do we map the virtual qubits in a quantum circuit onto physical qubits on real hardware? Now, as Yudong said, we can use orchestra in order to generate a wide variety of workflows. And within each of those workflows, we can vary different kinds of quantum computing resources that we might want to consume. And so the two main resources that we've investigated is circuit width, i.e. the number of qubits that are necessary, and circuit depth, i.e. the number of layers in the circuit. Let's start with the circuit widths. In the middle of this slide, I have a small table which shows the various integers that we tried to factor, and also shows the number of qubits that are required to finish the factoring problem after doing the classical pre-processing that Yudong described. Now, you might look at this and you might say, well, gee, Travis, I can simulate 3 qubits on my laptop. To which I would say, yes, you can. And that's actually a very good thing because it means that we can actually compute what the performance of an ideal quantum computer would be. And then that means that we can actually mod out the effect of quantum computing hardware from the overall success of VQF as an algorithm. So yes, the number of qubits is small, but the fact that they are small makes the circuit simulatable, and that's really helpful for us. Now shown on the right-hand side, I've reprised the connectivity map of Birdligan, and what I've highlighted are different qubit layouts, ways of mapping, say, the 3 virtual qubits for factoring the first integer in the table onto real hardware. And again, mapping to different physical qubits is important because different physical qubits have different associated single qubit error rates, different T1, T2 times, different C0 error rates between pairs of qubits. And so by changing the layout, we can again really investigate the performance of VQF on real quantum systems. At the bottom of this slide, I have a pictorial representation, of the QAOA ansatz. So within QAOA, there's a tunable sort of hyperparameter, one might say, called P, which changes the number of layers in the ansatz. And for every layer that we add, we gain two parameters, beta and gamma. And so by changing the number of layers in the ansatz, we change the number of parameters, we change the overall kind of complexity of trying to optimize the parameters of that circuit. And that's what we should think about when Yudong had his slide from earlier on, in the middle of that kind of iterative loop from a classical computer over to a quantum computer, and so on and so forth. A classical optimizer is going to try and optimize the parameters of that QAOA ansatz. And then once that optimizer has converged, we can measure that state that we have now prepared and get some bit strings back. And then we can check whether or not those bit strings encode the correct prime factors. And this is also worth keeping in mind that checking whether or not VQF has succeeded is trivially easy for a classical computer to do. Namely, you just multiply the two proposed prime factors together and see if you got the integer that you were trying to factor. Now, our initial investigations revealed that some very simple and common noise models do not always adequately model the behavior of VQF on Berbligen. So let's consider that 3-qubit problem instance, and let's consider a 3-layer QAOA ansatz. What we're showing on the right-hand side of the plot in the columns is the optimization landscape as a function of which layer we are examining. Remember, within each layer, we have two parameters, hence the grid is two-dimensional. We fix the parameters from the previous grid, or from the previous layer, excuse me, using a grid search. And what we notice in the rows is that we look at an ideal simulation, we look at a noisy simulation using noise models that are made available via Qiskit, and then we look at results from actually running on Berbligen. And again, this is where I think it's really important to emphasize the fact of the integration between Qiskit and Orchestra, the fact that we can take advantage of these kinds of simulation features, noise models, etc., available in Qiskit. And if you look at layer 3, you'll notice a discrepancy. You'll see that on the Berbligen system, there are these wiggly lines in blue that do not show up in the noisy simulation. And that suggests that the noise model is inadequate. And so in collaboration with Zapata, we developed a new noise model, which uses some knowledge about the hardware and the particular way in which 2-qubit gates are realized in IBM quantum systems to do a little bit of perturbation theory and derive a new noise model. And you can see on this new plot where we have the results from Berbligen at the top and the new noisy simulation at the bottom, we achieve much, much better agreement. And so given this, we know that when we do any kind of analysis of the performance of VQF, we need to take into account the effect of that kind of noise. So in my last 2 slides, I'm going to walk you through some of the results that we have, or additional results, I should say. So let's go back to that 3-qubit problem. What we're plotting on the y-axis is the success rate, i.e., what is the probability that a bit string that we measure after running QAOA successfully encodes the prime factors as a function of the number of QAOA layers, p. In blue is what we would get from a noiseless ideal quantum computer, and as one might expect, as we increase the number of layers, that success rate tends to 1. In red are the results from Berbligen, and then in orange and green are the results using those 2 different noise models. The green results are having a noise model that includes this ZZ coupling that we discovered in the previous slide was super significant for understanding the QAOA optimization landscape. And so this good agreement is very, very encouraging. But then when we actually go on to the 4 and 5 qubit instance, we discover something new must be going on. So on the right-hand side of the plot for 5 qubits, you can see that the simulations with the new noise model in green match well with Berbligen in red. But for 4 qubits, that is not the case, is it? And I'm not disheartened by this. It indicates to me that there are some additional noise sources that we should think about and seriously study. And this also really goes to highlight the value in running VQF directly on hardware to evaluate its performance. And so in our final moments, I will pass the floor back to Yudong, who will summarize the talk for you.
So given what we have learned so far about the hardware through the application of VQF, there's an argument that one can make about this being a distinct way of benchmarking that takes into account the distribution of circuit that arise in a given application context, as opposed to conventional benchmarking techniques that gauges the quality of quantum hardware for arbitrary unitary operations. And also earlier this year, Zapata team has also proposed a benchmarking scheme of similar nature for quantum chemical calculations, where we measure the fermionic length of a given choice to gauge its capacity for simulating strongly correlated electrons. There are, of course, pros and cons associated with this form of benchmarking. And we welcome further discussions on this topic from the quantum community. Also, we have a paper, so stay tuned.